there's a small number of strong acids. Therefore, weak acids are more numerous. And weak acids are weak electrolytes and vary greatly in their strength based on the amount of H3O plus that they produce. So on screen here, we see that we have a generic formula for an acid, HA, because it can donate a proton. We are still talking about a Bronsted-Lowry acid. We're going to mix it with water, and then since we're talking about a weak electrolyte, we are in equilibrium. So it's going to slightly dissociate to form H3O plus and A minus. And since we are in equilibrium, that means equilibrium calculations like those in chapter 13 are going to help us quantify the extent of acid dissociation, meaning how much did the actual acid dissociate, okay? And so a weak acid is going to only dissociate slightly to form ions in water. And so if we take a solution or dilute solution of a weak acid and we basically use it in an experiment so that we can show it to you visually, this is what we get. So we have our generic weak acid formula here, and this is before it dissociates. And then after dissociation, you see we have the amount of the weak acid, the amounts of H3O plus, and the amounts of its conjugate base here. Okay, folks? And what do we notice? We notice that we have a very small amount of H3O plus and the conjugate base, and they're both look relatively equal to one another. And we also notice that we actually still have a large amount of our undissociated weak acid. So what does that tell us about weak acids? It tells us that, guess what? It only took a small amount of ion dissociation before reaching equilibrium. So since most HA molecules are undissociated at equilibrium, then the concentration of our HA molecule at equilibrium is going to equal to the concentration initially of our HA molecule. And again, our H3O plus and our A minus are going to be equal to one another. And what do we notice? We notice that they're very small compared to the undissociated weak acid. And so because they're very small, they're going to also be very, very small compared to the initial concentration. Why does this matter and how can we verify this is going to be small? By using our equilibrium expression. So we have our K, C value, and that's going to be our products divided by our reactants. So we have H3O plus here, and then we have OH minus, right? We're going to divide this by HA, and of course by water. These are our reactants. If we have a lot more of HA, then of course our K value, our Kc value is actually going to be very small. Because say you have 1 here divided by like 100, right? Then our overall number is going to be very small. So since our Kc value is very small, that means we have way more reactants than products, which is explained in the overall expression here in our bar graphs, okay? Now we can start here and start layering or comparing and contrasting information between weak acids and strong acids. What do we see for strong acids? We saw that there was essentially no acid left, right? And it was all the dissociated ion. Therefore, the products were way more than the reactants, and so our Kc value was way larger. And that makes sense. When we're thinking about the strengths of acids now, we know that our K value, our equilibrium constants, can provide us knowledge about how large that K value is, and therefore tell us how strong that acid is going to be. So if you have very, very small K values, then you're thinking that you're dealing with probably weak acid at that moment. And then to further explain the difference of strong and weak acids, we can then react them with the metal. So we have a strong acid here, HCl Hope, for example, and then we'll see acetic acid, Dr. Strange, later on. But we also have a weak acid here. And as you can see, when we have a strong acid and you put a metal into it, it is going to react more vigorously because it has a higher concentration of H3O plus. And so you see a lot more bubble. Versus when you have a weak acid like CH3COOH or acetic acid, you see that there is very less bubble. Not saying that there's no bubbles at all. There's some here and there, but it's not reacting as vigorously because it does not have that higher amount of H3O plus concentration, okay? And so it will be much slower. So now when we think of H2S Spider-Man, we won't only just think of him as conjugate base paired with HS minus Captain America. Now we can specifically say, no, H2S Spider-Man is a weak Bronsted-Lowry acid. And so if I think of H2S Spider-Man, I'm going to think, okay, he has the ability to shoot his web fluid, right? Meaning donating a proton, for example, as a weak acid, but he's only going to use so much of the webbing. And of course, he's going to have most of it inside of him, right? So that's kind of how I think of, okay, as a weak acid, yes, he has the ability to donate a proton, but of course, he's going to keep it close to the chest at that point. Very similar to how the weak acids have the ability to dissociate, but they're still going to mainly be undissociated. So you can come up with any kind of way to think of that as well. And hopefully you'll use this to layer and compare and contrast on your flashcards too. So we know that if we have a weak acid and we mix it with water, it's going to slightly dissociate into these two ions, right? H3O plus and its conjugate base, A minus. And we also said that there's a K value, a K equilibrium expression, or an equilibrium constant that we're going to use to help express this. And that's going to be taking our products divided by our reactants. And we also said that this K value is way less than 1 or very, very small because we have a lot of the undissociated HA still in the reactants, okay? Now, let's go a little bit further. Can we simplify this expression? Yes, we can get rid of water and just simply put 1 because we know it's a pure liquid. And then we also can upgrade our K value. Instead of just calling it Kc and making it generic, we're going to upgrade it and call it Ka. Ka is now called the acid dissociation constant, okay? Acid dissociation constant, or you see it as the acid dissociation equilibrium constant. Either way, that A portion is saying that it's going to be an acid that is dissociating into its individual ions. Now, how much it dissociates, the extent is going to give us that K value. Now, we already know it should be relatively small for weak acids and larger for strong acids. So we're going to rewrite our equilibrium expression here. Ka is equal to H3O plus multiplied by the concentration of the conjugate base divided by the weak acid itself. So when you're going through and you're trying to use weak acids for calculations of equilibrium, your Ka expression must look like this. You must have H3O plus in the conjugate base on the product side and the weak acid in the reactants portion. Okay, folks? And like any equilibrium constant, this Ka value still is going to have a magnitude. It's still going to be temperature dependent, and it's still going to tell us how far right the reaction has proceeded. So how far in the forward direction has it proceeded to produce these products? We still are getting that same information from this equilibrium constant, okay? So again, the stronger the acid, the more H3O plus we're going to have, so a larger Ka value. And of course, the weaker the acid, the more HA or undissociated weak acid we're going to have, and so the smaller the K value. And it makes sense because strong acids are going to be such a high amount of H3O plus because it completely is going to be driven all the way to the far right, producing nothing but those dissociated ions, right? But moving forward, what else can we do with our equilibrium expression? Guess what, folks? We can use a p-scale here, just like we did before. So we can take our Ka value, we'll use a p-scale, and we'll get pKa. And our pKa, because we're taking a p-scale, is going to be negative log of whatever your Ka is. And so if you're telling me if I have a large Ka, I'm going to have a strong acid, and a small Ka, and I'm going to have a weak acid, then if I'm using my p-scale here, I can start creating rules for myself and start creating trends and patterns. And that's exactly what we're going to do. Okay, so pKa is going to be equal to negative log of Ka. And then we also know if we want to just get Ka by itself, we can take 10 raised to the power of negative pKa. Very similar to what we did for pH because we are using the p-scale. Okay, folks? So let's go ahead and write the trends out that we get just from knowing this information. So our Ka values are going to indicate the acid strength. Again, if you have a strong acid, you're going to have a very large Ka. If you have a weak acid, you're going to have a very small Ka. What else does a strong acid mean? It means that you're going to have a higher concentration of H3O plus versus a weak acid where you have a small concentration of H3O plus. And then finally, because we're using a p-scale, we're trying to take numbers that are very, very small and numbers that are very, very large and put them on a particular scale, making it easier for calculation. So if I have a strong acid that has a very, very high, large Ka, when I take the pK of it, the pKa will be very small. So strong acid, large Ka, therefore, when I do the p-scale, it's going to end up having a smaller pKa. And then vice versa for weak acid. You're going to have a small Ka. When I take it on the p-scale, the pKa value will increase. So small Ka, increase or larger pKa. A lot of times when it comes to memorizing this stuff, I always say memorize one of them and just think the other is going to be vice versa. So for example, I'll memorize everything for the strong acid when it comes to Ka. And I know that anything that's opposite of that or vice versa has to do with a weak acid. Whatever it takes to help your brain recall that information and get things produced, okay? So I just told you that we have a lot of large and small Ka values, right? So acid dissociation constants of weak acid can range over many orders of magnitude. Here are some like benchmark Ka values. So we have, when you have a high Ka value, a medium or moderate level of Ka, and a very low Ka. So I'm like, okay, you have high here, then you have medium, and then you have low. And then we have the percent dissociation when you just have 1 molar solution of the weak acid. So with the 1 molar solution of a weak acid with a very high Ka, you're going to have about 10% dissociated. So this HA is going to dissociate into H3O plus and, of course, the conjugate base by 10%. When you decrease the Ka value to a medium level, say 10 to the negative 5, for example, then that 10% is going to decrease to 0.3%. And then when you have a very low Ka value, as you can see, you only have 0.001% dissociation, so it gets very low. And from knowing this, of course, we can build trends. So for solutions with the same initial weak acid concentration, the smaller the Ka, the lower the percent dissociation. Just like we see here, the smaller the Ka value, the lower the percent dissociation. And we do have some examples of this of weak acids that, of course, have a relatively high Ka versus a low Ka, like HCN here. Hydrocyanic acid is going to have a lower Ka versus chlorous acid, which have a relatively higher Ka. These still are all weak though. Okay. We then can form a larger pattern or trend that weaker acids, and again, I'm applying this to what we saw before, right? We saw that we have a smaller Ka, that means we're going to have a larger pKa for weaker acids. We could also add in that we're going to have a lower H3O plus concentration. Now we're layering in more information. When you have a weaker acid, you also are going to have a lower percent dissociation of that HA or weak acid molecule. So if I was to write this down, I'll say weaker acids are going to have lower H3O plus concentrations, meaning they're going to have smaller Ka values, larger pKa values, and of course, lower percent dissociation. And then everything for stronger acids are going to be vice versa. So a stronger acid means that it can have a higher percent dissociation, larger Ka, smaller pKa, and probably a higher percent of H3O plus as well. Okay? And so as you see I'm not saying weak, strong. I'm saying weaker, stronger, because now we know that the weaker acids also have some kind of spectrum to it. So again, we have to layer that information on to help us. Here's some other Ka values of weak monoprotic acids. Monoprotic, it means that they're only going to donate one ionizable proton, and it's kind of in red here. And so we have the formula names for them, and we have their Ka values and their pKa values, okay? So depending on the Ka value, of course, that's going to tell you whether the pKa value is small or not. So if I see a very small pKa value, automatically in my head, I know that it should have a larger Ka value. If I have a very large pKa value, I know the Ka value is very small, and it probably is going to be dealing with these weak acids, but they're all on the spectrum, right, of acid strength. So do you have to memorize every single weak acid that you see here? No, we're going to get into types of weak acids next to help you just be able to classify them. But do you have to remember every single one? No. Again, what I do is memorize all the strong acids, and then anything outside of that is going to be considered a weak acid to me. I just have to be able to hone the skills of knowing the definitions from before and use that to my advantage. But either way, the purpose of this table is just to show you the varying ranges of Ka values and their varying pKa values. So is it going to be way easier using the P scale to just get these kind of numbers versus having to use these numbers that are in scientific notation? Okay, folks? Again, we know there's way more weak acids than strong acids. So my advice is to memorize the strong acids. Anything outside of that are going to be the weak acids. But to organize ourselves when we try to classify them, there are 4 different types. So first is going to be the hydrohalic HF, which makes sense because we had the hydrohalic, other strong acids, right? And then we were missing one single halogen, which was fluorine. And so we will get into more details as we go along in this lecture about that. But let's go ahead and talk about the hydrohalic HF as one of our weak acids. And one way I represent that is going to be with HF Falcon. So Falcon has a lot of different abilities, right? One is going to be flying and stealth, for example. So when I think of a weak acid, remember, it has the ability to donate that proton, but it's going to keep everything close to the chest. So when I think of Falcon or HF Falcon, I'm thinking, okay, it's going to donate a proton, but again, it's only going to strike when needed. Very set of subtle skills, right? So that's one type of weak acid, which is simply just one thing to remember. And then there are our H2S Spider-Man type of weak acids, which are going to be acids where the H atom is not bonded to oxygen or a halogen. So we're so used to seeing it bonded to oxygen or halogen. Well, there's 2 types of weak acids that we focus on that do not do that, which is going to be H2S Spider-Man and, of course, the HCN or hydrocyanic acid that we saw in the table before. Okay, so H2S Spider-Man, again, it's all about donating a proton but keeping it close to the chest, because most of the time for weak acids at equilibrium, we have a lot of undissociated acid, right? So with Spider-Man, again, the way I think of it, he has webbing. He's only going to use so much, but he's only going to use it in subtle times when needed. So that's already one weak acid and then two more. So far, there's only three. This is where it gets a lot of more numerous, which is going to be our organic carboxylic acids and our oxo acids. There's a lot more here. So of course we can't show you all of them, and I can't even give you an example for all of them. But I do have acetic acid, Dr. Strange. And one thing we notice about him is that he has a carboxylic acid attached to an R group. So we have an R group here, which we know is going to be an organic compound attached to COOH. So that's the reason why we have a specific group called organic carboxylic acids. You might have or see a carboxylic acid in other formulas, but if it doesn't attach to an R group, it's not going to be considered that functional group that we saw in chapter 20, correct? Now let's move on to our oxo acids. I am using an example of HCOOH or formic acid Ant-Man, okay? And it's pretty funny because, of course, ants in real life are going to release formic acid, so this just worked out perfectly. So formic acid Ant-Man is HCOOH. These are considered oxo acids. That means the number of oxygen atoms are going to equal to the number of ionizable protons, or it's only going to exceed by one single oxygen. So for example, there's two oxygens here, there's one ionizable proton. 2 minus 1 is equal to 1. So this fits the bill. It's only going to exceed by 1. If we have strong acids, we know they're going to exceed by 2 or more. So that's where the difference comes in here. Here we have 4 minus 3. That's also going to exceed by 1. And then here we have 1 oxygen and 1 ionizable proton. They're equal to one another. For formic acid, we also have 1 ionizable proton and then 2 oxygens here. Or sorry, 2 ionizable protons and 2 oxygens. So of course, we see that it has the ability to be equal, and that also fits the bill. Now, some people might say, well, wait, professor, hold up. I'm having an issue distinguishing them because they both have carboxylic acid. But remember, carboxylic acid, the specific functional group, is for organic compound. So the problem between these two, or the difference between these two, is going to be that R group. So the way we distinguish organic carboxylic acids is having an R group. And people might say, well, R group is a hydrogen. Well, hydrogen can be considered an R group if it's already attached to what? A carbon molecule. So when we're thinking of R group here, we're really saying we have a carbon-carbon bond that's forming, not a carbon-hydrogen bond. So that's one way to distinguish them as well. Now we're still talking weak acids. So CH3COOH, Dr. Strange, you can simply say acetic acid, Dr. Strange, has the ability to manipulate reality. But at the same time, he only can manipulate reality for a short period of time. And so think, he has the ability to give up and donate a proton, but only so much. He keeps his powers close to the chest. And then we have formic acid Ant-Man, or you can say HCOOH Ant-Man. And of course, one of the main things he can do is change size, right? And he can fit into many different situations. So the ability to change size, I just think of myself as donating a proton if he wants to switch sizes, bring it back. How long is he going to be not a small, ant versus having been a larger regular human being? That's how I kind of think of the proton donating. Most of the time, he is a regular size. He only needs to get into smaller size when it's in battle, and of course, it still has a time limit on it. So that's the way I kind of think of it. Here are all the types of weak acid. This is very, very important portion, because this is going to help us move through all of the equilibrium calculation that we have to do. And of course, everything we're going to learn about strong acids, you can now compare with your understanding of weak acids. Everything learned about weak acids, you can then compare back to strong acids. Use your flashcards in the best way you can to help you connect this information. And I'll say it one more time for the folks in the back. One way that I memorized this was by memorizing all the strong acids and bases, and then anything outside of that, understanding that those were considered weak acids and bases. And then I will go, now that I have more details about the types, I will go in and say, okay, now I can add in a couple of examples. So HF, H2S, HCN, those are pretty standard. You can write one example of acetic acid here. We see that a lot in lab too. Formic acid, HNO2, H3PO4. I will go off of definitions based on these three, okay? So just make sure that you do whatever it takes for you to remember.